Welcome back to the chemical bonding chapter. In the previous video we have seen about the ionic bonding. Now let us go for the covalent bonding. So we come across this covalent bonding because ionic bonding does not explain certain other concepts. That's why we consider this covalent bonding. When you consider this covalent bond, then we observe that the bond is formed by sharing of electrons from each atom so that each atom attains octet or duplet in case of the hydrogen atom. Suppose you consider this a hydrogen. So this bond is formed by the sharing of electrons. So this sharing of electrons takes place only when there are some unpaired electrons. For example, when we consider this hydrogen atom with one unpaired electron and another hydrogen atom containing one more unpaired electron, when these two electrons are shared, then they will form the bond between the two hydrogen atoms. Similarly, when you consider this oxygen atom, there are actually 6 electrons present. Similarly, if you consider another oxygen atom with 6 electrons, then 2 electrons between these two are shared so that oxygen atom links with another oxygen atom by means of a double bond. So when you consider this double bond, it is nothing but the 2 pairs of electrons like this. So one pair from this one and one pair from this oxygen atom is actually shared between the two, so that it gives rise to oxygen. Similarly, when you consider this nitrogen atom has got 7 electrons, 5 electrons. Similarly, another nitrogen atom having another 5 electrons. So between these two, when they share 3 electrons each, then we observe that there will be 3 pairs of electrons present between the two nitrogen atoms with 1 pair of electron on each atom. So when you look into this one, in case of the hydrogen atom, they attain the duplet. That is, in the first orbit capacity is 2 electrons, that's why it actually gets 2 electrons. In case of this one, this pair of electron belongs to this oxygen atom as well as to this oxygen atom. So that each oxygen atom will get 8 electrons. Similarly, each nitrogen atom will get 8 electrons. So we can also write this hydrogen-hydrogen bond as a single line. Similarly, oxygen-oxygen bond as a double bond. Nitrogen-nitrogen bond as a triple bond. So this number of bonds, which are called as the multiple bonds, indicate the number of pairs of electrons shared between the two atoms. But when you consider this concept of Lewis and Langmuir, each atom should get either duplet in case of the hydrogen or octet in case of the other atoms. So that, but there are some molecules formed by the sharing of the electrons, that is covalent bonding, in which the number of electrons will not be exactly 8. For example, there are limitations. Octet rule is not followed by some compounds. For example, one type of molecule will have the less number of electrons. That is electron deficient species. For example, when you take this beryllium chloride, BeCl2, we observe that beryllium and chlorine, they are actually sharing 2 electrons each. Maybe chlorine having 6 electrons has 3 pairs. Similarly, this also has got 3 pairs, but beryllium has got only 4 electrons. So it is an example for the electron deficient species. Similarly, when you consider this boron trifluoride, boron with 3 fluorine atoms, it shares only 3 pairs of electrons, so that boron has got only 6 electrons, but fluorine may be having 8 electrons, like this. So such examples are actually called as the electron deficient molecules. Central atom is not having the 8 electrons, that's why it is electron deficient. In the second case, we have electron rich, that is more than 8 electrons. More than 8 electrons in case of the central atom. For example, phosphorus pentachloride, PCl5. We observe that phosphorus has got 10 electrons in case of this phosphorus pentachloride. So it is more than 8 electrons, that's why it is each chlorine atom will be having octet. But central atom phosphorus is having this more than 8 electrons, that is 10 electrons in this case. Similarly, we have got this sulfur hexafluoride, SF6, sulfur hexafluoride. So there are 6 fluorine atoms linked to this sulfur atom at the center, so that there are totally 12 electrons in case of this central sulfur atom. Similarly, iodine heptafluoride, IF7, which is a stable molecule. This iodine has got actually 14 electrons as compared to the 8 electrons. That's why it is electron rich species. So these will not follow the Langmuir-Lewis theory or concept, because bond is formed by sharing of electrons from each atom, so that each atom attains octet. Even though octet is completed, still they gain some electrons, so that they become electron rich species. In some cases, we have this odd electron species. For example, in case of the nitric oxide, NO, if you look into the number of shares of the electrons and the total number of electrons on this, the number of the bonds between the nitrogen and oxygen is 2, and there are 3 electrons on this one, and 2 electrons for this. So totally the number of electrons that are shared, the number of electrons will be odd. So such a species will not follow this Lewis-Langmuir concept. That's why we will consider some other theory, that is valence bond theory for the formation of the covalent bonds. So let us consider that valence bond theory to explain the formation of this covalent bond. So valence bond theory, in short, it is named as the VB theory. It has been first developed by Hitler and London. And then it has been modified by Pauling and Slater. So this valence bond theory considers the overlapping of the orbitals. overlapping of orbitals containing unpaired electrons. Unpaired electrons. So if the unpaired electrons are present in the various orbitals, when they come across with one another, they overlap with one another in such a way that their spins are opposite. Suppose you consider this hydrogen atom with one electron in the s orbital. Suppose it comes in contact with another hydrogen atom of the same electron. Then one of these electrons will get the opposite spin. So we get one hydrogen with this electron and another hydrogen with this electron. When these two s orbitals overlap, it will give rise to the hydrogen-hydrogen bond with two with paired electrons. One electron will have the positive spin and another electron will have the negative spin. So this hydrogen-hydrogen bond is produced due to S overlap. Similarly, when we consider the overlapping of various orbitals, we actually get two types of bonds. Two types of bonds. One type of bond is actually named as the sigma bond. Sigma. The other type of bond is called as the pi bond. Pi. Sigma bond is formed by the head-on overlap of the orbitals. So this sigma bond formation can be explained in case of the S and S overlap, or S and P overlap, or P and P overlap in a head-on manner. That means if the P and P orbitals are of the same axis, if they come across in the overlapping in the same axis, then they will result in the formation of the pi bonds, sigma bonds. For example, when you consider this s orbital with another s orbital, it always gives rise to SS overlap. That is sigma bond. Similarly, s orbital of the one and p orbital of the other, when they overlap, they will give rise to sp overlap. If you consider this pp overlap, let me take for example px orbital with one more px orbital. Is not actually restricted to px and px. They may be py or pz orbital also. But the condition is they should be in the same axis, or they should collide, they should overlap in the head-on manner. Let me take this px orbital for example. If this px orbital overlaps with another px orbital, as I told you, it may be py also, pz also in the same axis. Then it will result in the formation of PP overlap. So this PP overlap will also result in the sigma bond. But if you consider this pi bond, if already there exists a sigma bond, then the remaining p orbitals may overlap laterally. Say for example, if I take this oxygen-oxygen bond, as I told you, there is a double bond between the two oxygen atoms. If already there is a sigma bond, that is due to the overlapping of the pp orbital in the head-on manner, then another p orbital containing the unpaired electron will undergo lateral or sideway overlapping. So this pi bond is produced by the sideway or lateral overlapping. If already, as I told you, if already there is a sigma bond existing between the two atoms, if there is a p orbital containing the unpaired electrons available in the other p orbital, then the lateral overlap will take place between the two such p orbitals. Let me take for example this as py or pz. If already sigma bond is existing due to the overlap of the pp orbital, then we can consider this py or pz orbital overlapping laterally. This will result in the formation of a pi bond like this. pi bond. Due to pp lateral overlap. Lateral overlap. Let me take for example in this case of oxygen. One p orbital containing the unpaired electron will undergo head-on overlap to give rise to sigma bond. The other p orbital containing unpaired electron will undergo lateral overlap to give rise to pi bond. That's why this double bond always consists of one sigma and one pi bond. If you consider this nitrogen triple bond. In case of this nitrogen triple bond, one pp orbital will give rise to sigma bond. The other two p orbitals overlap laterally to give rise to pi bonds. So usually we consider this triple bond consisting of one sigma and two pi bonds. So this is how the orbitals overlap to give rise to the sigma and pi bonds. Since sigma bond is overlapping to give rise to a strong bond, so comparing to the pi bond, sigma bond is always a strong bond. In a multiple bond, the pi bond will be opened first, then the sigma bond. Similarly, in case of the nitrogen molecule, the two pi bonds will get open first and then finally the sigma bond, if at all there is a breaking of the triple bond. So any such molecule produced due to the formation of the covalent bond is called as the covalent compound. So the covalent compound can be explained by the overlapping of the orbitals. According to Hitler and London, which is actually modified by Pauling and Slater, the orbitals containing the unpaired electrons overlap to give rise to a sigma bond. So each atom will contribute one electron. So that sharing of the electrons takes place between the two formation of the bond. For example, if SS overlap takes place, it gives rise to the hydrogen sigma bond. Similarly, sp overlap in case of some compounds, for example hydrogen and chlorine, sp overlap will give rise to sp sigma bond. In case of the carbon sigma bond, pp orbital overlap take place to give rise to sigma bond. For the multiple bonds, if already sigma bond exists, then the other p orbitals containing the unpaired electrons will undergo overlapping to give rise to the pi bonds. Sigma bond is always stronger as compared to the pi bonds. There are some characteristic properties of the covalent compounds as well as some bond characters also that we will consider in the next video. Thank you.